permutations and specifically the word problem. So up till now, we've looked at some really basic stuff with the fundamental counting theorem, and we've done all the algebraic stuff up here. So let's actually get to some word problems. And as I started off, usually this is how I start, this lesson in class. This is a little quick quiz as to what should we call this right here. And more often than not, everyone says something like a locker lock, or it's a lock. And some people will be more specific and say, hey, that's a combination lock. That's what we call them, outside the math class. However, realistically, this is not a combination lock. It should be called a permutation lock. Okay, and why should we call it a permutation lock? Well, a permutation is a list of things in a definite order, i.e. orders matter, or there's not orders, order matters. So for instance, if you have a combination that, and I have to be careful here, so if your locker code is 1531-2, you need to put it in this order, okay? This is a single permutation. So this is a permutation of those numbers. So for instance, if I tried to use 21531 on this locker, it would not open, okay? It would remain locked. Even though I'm using the right numbers, they have to be in a specific order, okay? So the basic idea is that this is the same combination of numbers. 1531 and 2, when I say those numbers, it does not matter what I say them in when we're talking about a combination. When we're talking about a permutation, that is saying that there is that order, like that is that like there are a specific way that we have to represent that those values or those things. So permutation orders matter. So another example here, AB is one permutation, BA is another, whereas that is just a single combination. When we talk about combinations, this and this are the exact same thing, whereas those are two specific things with permutations. So we have basic permutation questions where basically we have some population or some set and we are permuting the whole thing. So you've got 13 students in a class and 13 desks. How many different seating plans are there? Well, that's just a basic factorial. There are 13 factorial ways to arrange those students. Why? Because when you're thinking about who's going to go in the first desk, you have 13 options. When you think about who's going to go in the second desk, you have 12 options, and then 11, and then all the way down to 1. And you multiply all those together. Well, what is that? That is just a factorial. Same thing here. If you have 5 different cars parked in front of a building, how many different ways are there to arrange the cars in a line? That's just 5 factorial. You are taking your entire set and you are figuring out how many different arrangements there are. And finally here, a class of 30 students has to line up for recess. How many different ways are there for them to line up? Well, there's 30 factorial ways for them to line up. Again, first person in line, there are 30 different students who could be that first person in line. And then there are 29 different students who could be the second person, and then 28, and then all the way down to 1. And again, because we're linking those statements together with and, we're using our fundamental counting principle, we are using a factorial then to represent that. So, and by the way, when we actually get into notation, I'll wait. I put it in. I won't break my lesson order here. So these are the most basic of permutation questions. You've got some set, and you are permuting the whole set. We can make things a little bit tougher when we talk about objects in the set being identical. Okay, so if stuff is identical, there's going to be some permutations then that we cannot tell the difference between. So for instance, if I flip these two blue circles, that is a different permutation. I have switched two things. However, I cannot tell that I have switched two things. So when we have sets that are identical, I need to actually divide out all the different permutation of those identical things. So in this case right here, 1, 2, 3, 4, 5, 6, 7, I've got 7 things. There are 7 factorial ways to arrange that set. But there are 3 identical blues and there are 4 identical reds. So I divide out that stuff, those permutations, because I cannot tell the difference between them. I cannot tell the difference when I switch these blues or this blue. I can tell the difference if I switch a blue and a red. Sure, I can see that being something specific. That's why I still have a large number of permutations. But there are still now a bunch of permutations that look the exact same to me. And so here's a couple of different examples. The classic example is where you permute just like the letters within a word. So I'm going to look at this right here. So I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 letters in the word Mississippi. So Mississippi is like the classic example. So if I have 11 letters and I want to figure out how many different ways there are to arrange them, there are 11 factorial ways of arranging them. However, these I's, I cannot tell the difference between. So I've got 4 I's here. So I have to divide out the 4 factorial permutations that have just the i's being switched around because they look the exact same to me. And then I've got I've got p's here, don't I? So I've got 2 p's that I cannot tell the difference between. So I'm going to divide out the 2 factorial p's, and I've got 4 s's that I cannot tell the difference between. So whatever this evaluates to, by the way, I don't have a calculator on me, so I'm just going to leave it in these factorial forms. Whatever that evaluates to, that is how many different permutations there are. And in class, we did it with our names. Another tougher way that these questions can be asked sometimes is sort of these situations where how many ways can you get from point A to point B on a grid? And this might look superficially quite complicated because you're like, oh, wow, I'm going to go down and to the right all these different ways because I could start this way. So like this is a valid way of doing it, or I could do this way. Oh my goodness, how could I possibly count all the different ways? Well, when your instructions, and remember, we're still limited by only going down and to the right, because I'm limited by that, I can view this as actually just a really weird word, because no matter what, I'm always going to go down 3 times, and I always go right. What is that, 7 times? We count these, 1, 2, 3, 4, 5, 6, 7. So it doesn't matter how I get from A to B, I always have the exact same instructions mixed up. And those instructions are, I'm going to have 3 downs, and I'm going to have 7 rights. So I have 10 moves in total that I always do, and of those 10 moves, 3 of them are downs, and 7 of them are rights. Okay? And that's how I figure out how many different ways there are to get from point A to point B. And there's a few hundred, but it's not nearly as many as you would think, considering like the magnitude of this question at first glance. So these are what I would call the most basic of our permutations. We've got a whole set. We figure out how many different arrangements there are, or we've got the whole set and there's identical stuff within the set that we're switching around. We get a little bit more complicated when we are only permuting certain things in the set. So for instance, if we have 10 runners in a 100-meter dash, how many different ways are there to write the first, second, and third place results? So when we think about this, there are 10 factorial ways for the entire race to be completed. And there are 7 factorial ways to look, there are 7 factorial ways for the last 7 to be arranged from there, okay? So I have to remove all those, and I have to think about like what this list is going to look like. Now, normally when I teach this, I'm going to start off by just saying, okay, we've got 10 options for first place, 9 options for second, 7, or well, that's not how you count, 8 options for third. And there's nothing wrong with this. This actually is the right number, 10 times 9 times 8. However, this is something that's so important. We actually have a notation for it. This is a permutation where we have a population and we're permuting our things, okay? Or we have some number in the set, and this is how many we are taking out of the set. So using this as a previous example here, you would say this is 10 permute 3. And you would plug it in. You would say 10 factorial over 10 minus 3 factorial, or 10 factorial over 7 factorial. So let's look at some of this right here. We've got 5 names on the ballot for 3 positions, and those are distinct positions, so that's clearly going to be a permutation. So this is going to be 5p3 or 5 factorial over 5 minus 3 factorial. Here we have 12 songs on an album, and we want to use 8 of them, so this is going to be 12p 8, or 12 factorial over 12 minus 8 factorial. Let's look here. Oh, here we have a little bit of an algebraic problem where I'm going to solve it. I think I did this up above already, so I'm going to, in the previous video, so I'm going to skip this. We already did some examples like this. By the way, when I say I'm going to skip it, I don't think it was presented like this, but we did a problem where I would actually say, I gave it to you in this form. So let me plug it in, and then I'm not going to bother doing the whole thing. But n factorial over n minus 3 factorial is equal to 60. And then this is from the first video. So like I'm just taking this and plugging it in. I think you end up with a cubic here, so we use Desmos to solve, but this is essentially from the previous video. This video is already running a little long, so I'm going to stop here, and we're going to do cases in the next video and the other higher degree questions.